Here's a tree diagram for the action of flipping a coin and then rolling a six-sided die. We can go ahead and write the outcomes below the die numbers. Okay, which of these events would be a simple event? H1 and the event of tossing a heads and rolling an even number. So as you can see, H1 only appears once in the tree. So for that reason, it is considered simple. However, the event rolling an even number and tossing a heads, there are three possibilities for that. For that reason, it is not simple. Keep in mind that even though the coin toss has two outcomes and the die roll has six outcomes, how many outcomes does the actual overall experiment have? And so we could count them, just by looking at what I had written at the bottom. H1, H2, H3, H4, H5, H6, T1, T2, T3, T4, T5, T6 are all outcomes. So there are actually 12 outcomes in total. Now, how do you take the numbers 2 and 6 and make 12? Well, intuition may tell you that you have to multiply the ways that the first action can come out times the ways that the second action would come out. And that's how we find the total number of ways that this thing will happen. It's actually 2 times 6 is the way that we make 12. And just the reason why is because we're taking a tree here and putting it onto another tree, and you can see hopefully why it's a multiplication situation. It's 6 times 2. So that is the fundamental counting principle. If one event can occur m different ways, and a second event can occur in n different ways, then the number of ways that the two events can occur in sequence will be m times n. Now that rule could be extended for any number of events occurring in sequence. And why is this so useful? Well, we try to introduce the trees with simple examples to start with, but when we actually do probability and statistics problems in the real world, often deal with very large numbers of outcomes. And so the fundamental counting principle would allow us to find the number of possible outcomes without drawing a tree. Okay, so let's take the case that a coin is flipped 3 times. Can we find the number of ways that the thing can occur? So first off, I'll draw a tree for this one. The reason why is it's going to be small enough that drawing a tree is not too difficult. That is a tree for 2 flips of the coin, but now we want to flip it a third time. So let's put another H and T off of each branch. Okay, if we count the last column there, see how many different branches there are, we'll see that there are actually 8. So how do we compute that mathematically? Well, First, you write down the number of ways the first action can occur, times the number of ways the next action can occur, and then times the ways that last action can occur. So there are 2 ways that the coin can land on the first flip. There will be 2 different ways that it can land on the next flip. That makes a total of 4. And then we'll multiply by 2 once again to get our total of 8. That's using the fundamental counting principle. So 2 times 2 times 2 is 8. We could also take advantage in this situation of the fact that it's a repeated action, and we could actually write it in exponential form, which would be 2 to the 3. That would also be 8, of course. Now when it comes to drawing a tree for a 6-sided die being rolled twice, it's going to be quite a few branches. We can see why here. First of all, you got to do 6 branches for the first roll, and then off of each of those you got to have 6 branches. As you can see, this is going to become quite tedious and difficult to draw, so I'd rather not draw it here. I'll just draw the start of it. But basically we're going to have to take the second roll and put it onto each of the outcomes of the first roll. So what would our blanks look like in this situation? We put 1 blank for the way the first one can come out, and then multiply by another blank here. And we just have to put the right numbers in the blanks. There are 2 total actions. So there are 6 ways the first roll can happen, and then when you roll it again, 6 ways again for the next roll. That makes a total of actually 36, and that would be our final answer there. In exponential notation, it would be 6 to the 2. Now, when we go to flip a coin 8 times, we are certainly not going to want to draw a tree for that. The branches would just take up the whole page. So let's follow the pattern above by putting a blank here for the first flip, a blank for the second flip, the third flip, the fourth flip, the fifth flip, the sixth, seventh, and the 8th. Now, what would go in those blanks for a coin? Well, there's 2 ways the first flip could happen, 2 ways for the next flip, and 2 for the next, and so on, and so on, and so on. Now, to write it in exponential notation so that we don't have to type all that into the calculator, we're going to want 2 to the power of 8. Okay, and we'll try that here on calculator. And let's see what our calculator says. It says 256. Definitely not a tree that I would want to draw. Okay, so 256 different ways it can come out. Now let's try a 6-sided die being rolled 4 times. First off, I'll start by putting 4 blanks down just to get myself ready to put the numbers in, because there's 4 actions. Then I have to decide what number is appropriate. Well, it's a 6-sided die, so there's 6 ways that the first roll can happen, 6 ways for the second roll, 6 ways for the third, and 6 ways for the fourth. So we actually want 6 to the 4, and that is 1,296. So hopefully you can see here why the fundamental counting principle can be helpful.